Welcome to the Chapter 12 lecture for the Management 3120 Operations Management course. I am Dr. Bill Perkins, and I'm going to provide you a video lecture based on the material found in the textbook Practical Operations Management, 2nd edition from Natalie Simpson and Philip Hancock. Our objectives for this chapter is to define lean operations. We're going to identify the mechanics of lean and explore the principles of lean. So let's get started. An operation is said to be lean if it is operating with minimal waste of any kind. At first, it might seem ironic that an organization would strive for anything else, but the mechanical principles and underlying philosophy of lean operations are relatively young, beginning with Toyota Motor Company's innovative transformation of production control and inventory management starting in the 1950s. Lean operations are now practiced worldwide by many types of organizations. And just-in-time is an earlier and alternate term for lean operations, in which a system implicitly operates with minimum of inventory and waste. So, reorder point systems control production activity by monitoring inventory levels, reacting when the stock available drops to a certain minimum level, known as a reorder point. It is not known precisely how old reorder point systems are, but some of the oldest examples of written language are 5,000-year-old Egyptian and Sumerian inventory records. Further published descriptions and analysis of reorder point systems have been available for more than a century. Traditional reorder point systems are examples of implicit and signal-based planning, meaning that their operations requires only that participants understand the minimum levels to watch for. There are no specific instructions concerning when to take that action. Traditional reorder point operations are also known as a pull system because it also allows demand to consume existing inventory and then reacts to the lower stock level by ordering replacements, pulling new inventory into the system. So for definition purposes, a pull system refers to a production system that reacts to signals of demand, relying on internal coordination instead of the implementation of explicit plans to achieve outcomes. And material requirements planning, or MRP, emerged in the 1970s as an alternative to pull-style inventory management. MRP combines information on product structure and current inventory levels with forecasts of future demand, calculating precise amounts and exact timings for orders of raw materials, components, subassemblies, and finished goods. These explicit plans for all items in production are called planned order releases, providing detailed answers to the questions of how much and when any certain item should be ordered. While the older reorder point systems are considered pull systems, MRP-based systems are often referred to as push systems. MRP relies on central planning to calculate and distribute instructions to everyone involved in production. In that sense, the production system is pushed to act by the central planner instead of being triggered to act by dropping inventory levels. Moreover, in a multi-staged environment, when an order for any item is finished, it is then moved or pushed to the area where it will be processed next. In the more passive reorder point system, orders simply wait wherever they are to be relieved by users as needed. So also for definition purposes, a push system is a production system that calculates and anticipates demand, relying on the implementation of explicit plans instead of internal coordination to achieve outcomes. Toyota Motor Corporation faced daunting financial, technological, and competitive pressures during the 1950s. This organization and era are now widely recognized as the genesis of what would become the youngest of the production systems, illustrated here in Figure 12.1. To address its early difficulties, Toyota sought to make the absolute most efficient use of its resources, eliminating any unnecessary inventory or activity within its production system. Ideally, any operation would only produce exactly what was needed, exactly when it was needed. It would produce one at a time, only when requested, and only when nothing was otherwise available in stock. The Toyota production system that evolved over the next 3 decades gained global attention under the more general name of its just-in-time, or JIT, in the 1980s. While this approach to production was always lean, the terms lean and lean production followed afterwards. Now, today's vision of lean, or version of lean, resisted the separation of planning from production that had grown with the popularity of MRP systems. Contrary to the heavy emphasis on explicit push-style schedules, lean production emphasizes implicit signaling to trigger production only when needed. So this approach is not only another form of a pull system, it can be argued to be a return to the traditional reorder point approach illustrated at the top in Figure 12.1. Although a just-in-time lean system is by definition a form of reorder point system, it is a very particular reorder point system in which the reorder point has deliberately been set to 0 or near 0. Now, how Toyota created a production system whose success is based on the fact that it only reacts when it is on the verge of running out is explained by both the mechanics of the system and the philosophy that governs it. Being the youngest of the production systems, lean operations are often formed from some older system, similar to how lean production resulted from Toyota's self-study over a half a century ago. Creation of a lean production system, whether original or transformed, requires an understanding of the internal mechanics of a pull-style operation. Specifically, to implement lean production, organizations must adopt the following mechanical principles. First, they must plan smaller lot sizes to support lower inventory levels. Next, they must employ effective signaling to support implicit planning. And then finally, they need to smooth production to support efficient operations. Now, a more traditional approach to ordering focuses on identification of economic order size, regardless of whether this amount is large or small. This perspective seeks economies of scale, which entails decreasing average unit cost by increasing the volume. Now, increasing in order size, if it reduces the overall cost of inventory policy. So efforts to reduce fixed costs associated with ordering and replenishment can take on many forms depending on the situation. Now, these common improvements reduce the value of fixed costs. First, eliminating the paperwork traditionally associated with ordering and receiving through electronic data interchange, which is known as EDI, with suppliers, and streamlining ordering, stocking, retrieval, and handling through barcoding and radio frequency identification, RFID, RFDI, sorry. RFID, that's correct. Tagging of inventory. Investing in the process of machine setup to make frequent changeovers quicker and more efficient is the last one. So we're going to move on to a lean system requires as little as possible and only when necessary. The ideal lean order size is 1 unit, being the theoretically smallest possible amount of anything that can be acquired. However, ordering and delivering some item one by one is seldom practical in reality, And keeping lot sizes at a practical minimum should not be pursued without having investigated two related issues. First, the potential reduction of any fixed costs associated with ordering and preparation for the frequent deliveries that will result from smaller lot sizes. Now, if order sizes from suppliers are reduced to minimal amounts, then delivery of new orders from suppliers becomes more frequent. So to function well, a lean system must accommodate these frequent deliveries and should consider making the following changes as well. First, they need to eliminate the warehouse. Many organizations maintain a warehouse to receive and store large shipments of raw materials and supplies. If such an organization plans to go lean, it might consider eliminating this facility and arranging for smaller deliveries to be made straight to the production facility itself. Next, deliver directly to the user. A small order for replenishment should ideally be delivered to where it is needed instead of an official reception area to be retrieved after its arrival. The smaller and more frequent the ordering, the more time the user spends retrieving these orders from an older style reception area, and thus the user would have less and less time for production. Finally, the reduced time leads. Cultivating relationships with local suppliers and seeking more efficient means of small order transportation and handling can greatly reduce lead times, meaning reducing the delay between requesting a product and actually receiving it. So for definition purposes, electronic data interchange, or EDI, refers to the linking of two information systems from two different organizations to transfer data and conduct transactions. And for definition purposes, radio frequency identification, or RFID, refers to the tagging of objects with devices that may be detected and interrogated for information by remote electronic readers, allowing identification and tracking without contact. Frequent delivery of small orders directly to users within a large facility can create complex traffic patterns unknown to an older style operation. Once an elegant solution for enabling the frequent delivery supporting work along a production line is illustrated here in figure 12.3 on this slide. Now here, the U-shaped cellular layout replaces the traditional linear layout, which is illustrated at the top of the slide. This revision allows the supplies required by each workstation to be delivered to a single central point, eliminating the need for delivery traffic to move back and forth across the length of a traditional layout. A cellular layout has a variety of advantages, but one benefit attractive to lean operations is its ability to shape supply traffic patterns such that they are less likely to interfere with themselves and with the operation of the line. Now, although the industrial principles of lean operations were first popularized by automotive manufacturers, small firms with perishable goods have long used similar techniques to operate with a minimum of stock. As an example, bakeries often use bin-based signaling systems to control replenishment, such as the one pictured here. When one bin of time-sensitive product is emptied by demand, this signals the bakery or the baker to create another small batch. Now, in the case of very large items or large containers of items, footprints can be painted on the floor to outline where the item should rest while waiting inventory. If a worker sees an empty bin, empty shelf space, or an empty footprint on the floor, the worker can then take action to fill it again with that item. Exactly how much of that item is sitting idle in inventory is loosely determined by the organization by deciding how much bin capacity to label on behalf of that item. And reacting to an empty bin by refilling it is a good signaling system, provided that the person or people who could refill the bin can also watch it while production is underway. However, if the inventory is not stored in the same area where it is created or stored across several locations for easy access by multiple suppliers, the builders of that inventory will not be able to monitor the state of all the bins effectively. This problem is typical of any large production plant and one that is readily solved with another tool for signaling the Kanban. The Kanban is usually some type of a card, highly visible, transportable, and readily recognizable for everyone involved in the production. Now, each Kanban is understood to be a signal of a bin inventory that's being consumed, and thus another needs to be filled to replace it. So for definition purposes, Kanban is a Japanese term for a signal, often a card. Kanban systems use these signals to regulate production. So when a Kanban is found by producing work center to the left of figure 12.4, it is attached to an empty bin, and that bin is filled with the inventory specified by the Kanban. This brightly colored work ticket then remains attached to the bin as it is transferred to some inventory storage area. Now, when the bin is later removed from storage by the consuming work center, its Kanban is detached and immediately returned to the producing work center to signal the need to create another bin of inventory. Now, if the producing work center cannot locate any cards returned without their bins, then the producing work center remains deliberately idle, as this is the signal that the system does not require any new inventory. Now, thus, while inventory is moving from left to right between the producing and the consuming work centers, as illustrated here in figure 12.4, the Kanbans are not following the same path. Rather, the Kanbans are circulating in their Kanban loop, traveling from producing work centers to the inventory storage area, and then returning repeatedly for reuse each time inventory is claimed for consumption. Now, design of the signaling system, as discussed so far, has assumed that only production needs to be controlled by the signaling mechanism. However, in complex production environments, the system designer may also wish to control the consumption of the item, particularly when multiple work centers or parties may have a reason to withdraw that item from the storage area, and these groups do not otherwise coordinate with each other. Now, in this environment, a second loop may be established, creating a dual card Kanban system as pictured here in 12.6. So, for definition purposes, a dual card Kanban is a Kanban control arrangement consisting of two Kanban loops. The first Kanban loop signals and limits the production of an item, while the second loop signals and limits withdrawals from consumption of that item. Now, finding a repeating pattern that blends product models into smooth sequence and enables mixed model assembly, or the use of a highly efficient assembly line to create a mix of different products. However, the challenge of mixed model scheduling and mixed model assembly isn't simply locating the smoothest pattern possible from various model requirements. Rather, the lean operation must confront why the traditional batch style scheduler judged the larger run sizes as economical and thus preferable. This returns to the discussion and the issue of reducing fixed costs. In this case, costs of switching between models, which the traditional scheduler minimized. So mixed model assembly is known as the production of a range of products with a single assembly line, primarily by varying features on an otherwise standardized product. Now, mechanical tools such as Kanban loops enable operation of a system, but do not in and of themselves ensure lean operations. So overall, lean operations is better described as the pursuit of an ideal state outlined by this set of a broader philosophical principle. We're going to start with eliminating waste. And also, too, I'll just cover all four of them: striving for visibility and flexibility in the system, pursuing closer relationships with outside suppliers, and then seeking continuous improvement. Now, each one of the mechanical principles discussed earlier is linked with one or more of these principles, providing a practical method supporting the philosophical argument. Since the mechanical principles are narrower in focus than the corresponding philosophy, limiting discussion to the tools alone would leave out much of the value of lean operations. So for definition purposes, we're going to talk about Muda. Muda is a Japanese term for waste, particularly anything a customer is not willing to pay for. And inventory, by definition, is idle value waiting for use, and it is the holding costs created by this idleness that the customer does not value. Reducing fixed costs, reorder points, and lot sizes supports the reduction of inventory levels. Now, safety stock is one kind of an inventory common to a traditional production system, yet particularly troublesome in the philosophy of lean operations. So contrary to the spirit of just-in-time, safety stock represents idle goods being held just in case. So this inventory is intended as protection against some uncertainty in the future, such as an unexpected surge in demand or a possible future failure in supply. Not only does safety stock represent Muda because of its idle costs, the philosophy of lean sees this type of inventory as hurting the system. So figure 12.8 on this slide illustrates an allegory often used to clarify how safety stock can hurt an operation even as it protects it. So here the production system is symbolized by a boat operating on a lake. The water in the lake is symbolic of inventory in the system. So the boat in the upper left-hand image of figure 12.8 is where the story begins, and the equivalent of a traditional system operating with high levels of safety stock. The high water level at the beginning of the story keeps the boat safely away from the hazardous rocks on the bottom of the lake, symbolic of the uncertainties from which production systems require protection. Now, lean operation calls for the equivalent of draining the lake, but this will then expose the boat to the hazards below. This is where traditional inventory management and lean philosophy take starkly different views. While the traditional view of the second image in figure 12.8 is one of the danger and crisis, lean philosophy considers the second image as a positive situation. At the beginning, the problems and uncertainties plaguing the system were hidden by the inventory levels. But now they are being exposed by carefully dropping those levels, with the most significant problems emerging first. Now, although successful operations are in jeopardy in the short term, these problems can now be named, confronted, and fixed. So in the allegory of the lake, this is the equivalent of destroying those rocks that have been exposed, allowing the boat to continue operating across the shallower, leaner lake. And it is tempting to interpret the allegory of the lake as a demonstration of the need to eliminate inventory in the pursuit of lean operations, but that is a dangerous oversimplification. Now, note that the Muda in figure 12.8 exists in the rocks, not the lake level, and thus the greatest achievement in the symbolic story is the removal of the exposed rocks, not the draining of the lake. So this demonstrates that successful pursuit of a lean philosophy does not dictate the elimination of inventory, but rather the elimination of the reason for inventory. So, for example, reducing fixed costs reduces the motivation to order or produce in large lot sizes, which naturally reduces inventory. Now, safety stock may be held just in case disruptions occur in deliveries from a distant supplier. Now, if this reason can be eliminated, such as by switching to a local source, then the safety stock is no longer necessary and can be eliminated. Now, visibility or transparency is a philosophical thread running through many of the different aspects of lean operations. Now, visual systems communicate information through their appearance, and even the concept of safety stock as Muda is partially related to a desire for visibility, as stocks of unnecessary inventory can literally hide problems in the system. Now, Kanban loops are an example of the lean operations preference for visual signaling, making visible the need to produce. So visual systems can be designed for signaling other types of information as well, such as an Anden systems that signals when assistance is required in a certain area. So an andon system signals when assistance is required in a certain area. However, the issue of visibility is not limited to what is literally visible to employees, as this principle applies equally to information in general. Now, in addition to vivid visual signals within its facilities, a complex lean organization likewise depends on investment in enterprise resource planning, otherwise known as ERP, to make remote facilities readily visible to one another. An ERP system maintains real-time data shared by different parts of an organization, allowing both better integration of functional areas like marketing and production and better visibility of inventory levels and activity across distant locations. Now, high visibility systems have an advantage of being able to keep large groups of people continuously well informed, which is a condition that promotes good situational awareness. Now, situational awareness is critical to successful pursuit of another broad goal of lean operation, that of developing and practicing flexibility. This need for flexibility was first suggested in the mechanical principle of mixed model scheduling, in which a lean system resists batching together identical production items, switching between different models during production instead. So situational awareness is an individual or organization's comprehension of surrounding environment and its potential near future states. So the rapid movement of minimum amounts of inventory through a lean system makes real-time inventory information critical. Wireless handheld devices are common tools guiding this type of inventory flow, such as the portable barcode reader, as you see here in this illustration. Not only does the device reveal detailed information concerning the contents of the box, it can remotely report this information to an enterprise resource planning system, ERP, supporting good situational awareness among all ERP system users. And a lean just-in-time operation requires many small deliveries, often creating more activity and greater pressure on purchasing in general. So for this reason, a lean system should develop a closer relationship with the supplier providing the deliveries, viewing that supplier as a partner in production. So such a relationship is often necessary to implement some of the just-in-time mechanisms, such as linking the two organizations' information systems through a paperless EDI ordering arrangement, or trusting the supplier to move unsupervised through the facility and deliver straight to the workers who are using them. To encourage the supplier to participate in this more rigorous arrangement, a lean perspective suggests that organizations consider a long-term sole sourcing arrangement with one supplier, rather than adopting the traditional perspective requiring various suppliers to continuously bid for the organization's business. Now, the pursuit of seamless supplier partnerships can even be taken to the extreme of inviting suppliers to locate operations within the lean operation being supplied, so that raw material inventory might travel in the smallest amounts over the shortest distances to arrive at the moment of use. This co-location and user of supplier was first popularized by the Bose company as just-in-time 2, suggesting it is as the next chapter in the development of just-in-time. So just-in-time 2 usually implies implementation of a broader arrangement known as vendor managed inventory, or VMI. So for the purposes of definition, just-in-time 2 is a phrase first popularized by the Bose company, emphasizing vendor managed inventory and co-location of those vendors within a production facility. Now, because lean operations are often created from existing systems that had operated previously under such an older style of production planning and control, outside consultants are often brought in to initiate the transformation of processes. Now, these consultants assess the operation for early opportunities to eliminate waste and educate participants on the underlying principles so that they may carry the transformation further. Now, the latter is critical because a lean philosophy sees the transformation to lean operations as never being finished. One compelling philosophical principle of lean is its emphasis on continuous improvement, or Kaizen. And Kaizen is a Japanese term for continuous improvement. Now, while improvement is desirable in any production philosophy, a traditional view of this process usually considers improvement as an undertaking separate from normal operations. So a system would proceed normally according to its design, but the organization might choose to improve upon that design periodically in a separate initiative, such as a project with a definite start and completion. Now, in contrast, Kaizen sees the process of improvement very differently as a daily part of the system's operation. So the result is a system that is constantly evolving towards an ideal state, but one that is likewise never completed designed. Or completely designed. Ideally, its evolution is guided by the participants in that system, often organized into teams of employees known as quality circles. So a quality circle is a group of employees that meets regularly to discuss and develop opportunities for continuous improvement of their operations. And quality circles meet regularly as part of the normal operation of the system, brainstorming the constant stream of new opportunities to pursue the spirit of continuous improvement. Now, alternatively, some of these employees may be selected for training as improvement experts to lead product for an ongoing Six Sigma program. And Six Sigma is a quality management program emphasizing the applications of analytical tools and widespread involvement of employees across the organization. And the particular compatibility between Lean's signature focus on driving out waste and Six Sigma's well-defined organizational structure has given rise to Lean Six Sigma, one of the newest methodologies for continuous improvement available to a business. It is an improvement methodology combining the waste reduction and process flow focus of lean operations with the structured analytics and project work of Six Sigma. And that concludes the Chapter 12 lecture. Please visit Blackboard for this week's expectations and deliverables. And I will see you in Chapter 13.